This notes video is going to be over titrations, the technique, and the math. So some important definitions we want to cover before getting into more technique and math is just in general what the purpose of a titration is. It is a method used to determine the unknown concentration of a solution by neutralization reaction, essentially. So we take an acid and a base with some known information and neutralize them until we reach the end point, which we'll talk about. So in this situation, there's going to be two different solutions. There's the titrant, which is the solution with a known concentration and volume. This is usually the base. It does not have to be, but typically in a titration, the acid is the unknown. And then the analyte is the unknown molarity. We will know the volume of the analyte in a titration, but we will not know the molarity. Again, this is usually the acid. The difference here is the titrant is usually in the burette, and the analyte is usually in the flask. The burette is a glass tube with fine graduations, and the stopper at the bottom to dispense liquids in small amounts. Now, there's a big difference in a titration between the end point and the equivalence point. The end point is where we end the titration because the indicator has changed color, and that tells us that the titration is over. The equivalence point is when the two solutions are actually equivalent moles. And because of the limitations of the indicator, it is not actually at 7, which is neutral, which is the equivalence point, that the indicator changes color. So the end point is actually a little bit past the point in which the two solutions are truly neutralized. So just going through again some of this vocab here, we have our acid, which will be our analyte in lab. That goes into the flask, and we know the volume. We just do not know the concentration. Then we put our indicator in. That indicator could be anything, but typically is phenolphthalein. And then we have our burette, which is going to contain our titrant, which is, again, typically our base. And we add it slowly until it changes the phenolphthalein indicator color from clear to that light pale pink or fuchsia. Now, when you're doing the titration, the palest pink is your goal because that's going to give you closest to the end point. Again, the end point is a little bit farther than you may want it to be in terms of actual neutralization, but the deeper pink it becomes, the more you've overshot and the more error you're introducing into your data. So in terms of calculations, the HCl solution of molarity is titrated with a 0.5 molarity NaOH solution. The titration requires a 75.8 milliliter of the NaOH solution to reach the equivalent point of 52 milliliters of HCl. So firstly, our titration equation, you'll probably think looks pretty familiar. Molarity of acid, volume of acid equals molarity of base, volume of base. And this is just the same as the dilution equation. If you recall, in the dilution equation, it works by setting moles equal to each other. That's the same case here. The difference of this equation, though, is that we do have to consider if our acids or bases are diprotic or triprotic. So we will also have to factor in the number of hydrogen ions in the formula and the number of hydroxide ions in the formula. Most of the time, as in this case, they are 1. So it really doesn't affect too much, but in future problems, we'll see that it does. So setting up our math here, we have the molarity of our acid, which is our unknown, the volume of our acid, which is 52.00 milliliters, and then HCl only has 1 H. Molarity of the base is going to be 0.50. volume of our base is going to be 75.8. And then the number of hydroxides here for NaOH is also 1. So again, if they're both 1, you can kind of just not include that into the equation. And then it really will look like our dilution equation, where we're having X on the same side with the number for the acid, multiplying our two pieces of information about the base together. And then finding X, which rounded to sig figs should be 0.0 or 0.73 molarity. Okay, the next one we'll see is a little different. So similar setup, molarity of acid, volume of acid, number of H ions in the acid formula, molarity of base, volume of base, number of hydroxide ions. So reading our problem, we see we're given information about the acid completely. We know both the molarity and the initial volume of it. And then we can see that it's HCl, which is 1H in that formula. For the base, we know that the molarity is 0.65. We do not know the volume, and we can see that there are 2 hydroxides there. So when setting it equal, we're going to have our 0.51 times our 20 times 1 and set that equal to 0.65 times X times 2. And if you recall, in our other problems, we would have doubled the molarity of the base anyway, knowing that it is having those 2 hydroxide ions. So this just ensures that we are accounting for that when we consider how much acid we need. We're going to need double the amount of acid to neutralize had it been NaOH. Solving for X and rounding to sig figs, we should get that we need only 8 milliliters of the base, which again should make sense because we would need double the amount of acid compared to base to neutralize. All right, the last example here, we have an equation. So I'm going to show you a different format of the same equation that you can use to solve. You can kind of pick which one you find more straightforward. So another way that you can write this equation is dividing it by the coefficient of the acid and dividing this by the coefficient of the base. For the most part, it'll work out in terms of if you're just counting hydroxides and hydrogens. In this one, obviously all the coefficients are 1, so it wouldn't matter anyway. But if you're given an equation, this is an alternative formula that you can use that'll still work. But I would recommend just kind of sticking with this one. So plugging in our information, we have molarity of our acid, we do not know. The volume of our acid being 24.5, the molarity of the base being 0.112, volume of our base 33, and hydroxides are 1. If they're both 1, I'm not going to bother really including them because they kind of just drop out. If one side has like a 2, like our last problem, and the other side has a 1, I still would like you to write the 1 in that case, since they are not canceling each other out. Okay, solving for X here, we should have an answer rounded to 3 sig figs of 0.151. That's a little close, 151 molarity. Hopefully that seems pretty straightforward after going through the dilution equation already. We will continue to review this in class.